Stellar mass black holes represent one of the most enigmatic endpoints of stellar evolution, forming when massive stars exhaust their nuclear fuel and collapse under their own gravitational weight. In our Milky Way galaxy alone, astronomers estimate there are between 10 million to 1 billion stellar mass black holes, each weighing between a few and 100 times the mass of our Sun. Despite their abundance, these objects remain largely hidden from direct observation, revealing themselves primarily through their gravitational effects on companion stars, or through gravitational wave events when they merge with other compact objects. The formation of these cosmic voids involves complex physical processes that depend critically on the initial mass of the progenitor star, its chemical composition, rotation, and other factors that influence its evolutionary pathway and ultimate fate. The journey toward becoming a black hole begins with a massive star burning brightly on the main sequence, fusing hydrogen into helium in its core through nuclear fusion. Unlike smaller stars like our Sun, massive stars with initial masses exceeding 20 solar masses progress through their life cycles much more rapidly, remaining on the main sequence for only a few million years before beginning their transformation. As hydrogen fuel depletes in the core, these massive stars continue their nuclear burning sequence, progressively fusing heavier elements, helium into carbon and oxygen, then proceeding through neon, silicon, and finally reaching iron. This progression represents a fundamental difference from lower mass stars, which terminate their fusion processes at lighter elements. The formation of an iron core marks a critical juncture in stellar evolution, as iron fusion does not produce energy, but instead consumes it, creating a scenario where the star can no longer generate the outward pressure needed to counterbalance the crushing force of gravity. With no sustainable fusion reactions to provide outward pressure, the iron core succumbs to gravitational collapse, initiating the final moments of the star's existence and potentially setting the stage for black hole formation. For the most massive stars in the universe, black hole formation can occur through a process known as direct collapse, where the stellar core implodes with minimal explosive feedback. In this scenario, the star's immense gravity overwhelms all forms of degeneracy pressure that might otherwise halt the collapse, causing the core to directly form a black hole without the dramatic expulsion of matter typically associated with supernova explosions. This gradual implosion process differs significantly from the violent supernova that produce neutron stars, as the collapse occurs more symmetrically and with less energy dissipation. One key characteristic of black holes formed through direct collapse is their minimal natal kick, the velocity imparted to newly formed compact objects due to asymmetric explosion mechanisms. While neutron stars frequently receive kicks of several hundred to around 1,000 km/s, black holes formed through direct collapse experience negligible velocity changes, as any shock waves generated during the implosion process are typically weak and largely symmetric. This theoretical distinction has found observational support in systems like V404 Cygni, where astrometric measurements suggest the presence of a black hole that formed with minimal natal kick, allowing it to retain a distant stellar companion that would likely have been ejected had a powerful asymmetric explosion occurred. Not all stellar mass black holes form through direct collapse. Many emerge following supernova explosions through a process involving material fallback. In this scenario, a massive star experiences core collapse that initially forms a proto-neutron star and generates an outward-moving shockwave. However, if the explosion energy is insufficient to completely unbind the stellar envelope, a significant portion of the expelled material fails to reach escape velocity and eventually falls back onto the short-lived neutron star. This accumulation of matter onto the neutron star increases its mass beyond the theoretical maximum supported against gravitational collapse, approximately 2 to 3 solar masses, forcing it to further collapse into a black hole. This fallback mechanism represents a delayed pathway to black hole formation and plays a crucial role in determining the final mass of the resulting black hole. Recent three-dimensional simulations of this process in a 40 solar mass zero-metallicity progenitor have revealed fascinating dynamics, where neutrino-heated bubbles can persist for tens of seconds after black hole formation before being accreted, transferring sufficient energy to the shock wave to allow it to propagate through the stellar envelope. The fallback process not only influences black hole formation, but also helps explain observed abundance anomalies in metal-poor stars and contributes to our understanding of the natal kicks and spins that characterize stellar mass black holes. Beyond the traditional pathways of direct collapse and supernova with fallback, several alternative mechanisms for stellar mass black hole formation have been proposed and studied. One intriguing possibility involves the transformation of white dwarfs or neutron stars into black holes through accretion processes. In this scenario, a white dwarf or neutron star in a binary system can siphon matter from its companion star, gradually increasing its mass until it exceeds the critical threshold for gravitational collapse. Another proposed mechanism is the collapse-induced thermonuclear explosion, CITE, where increased burning rates due to adiabatic heating of the outer shells during collapse lead to a thermonuclear explosion. This process naturally produces approximately 1051 ERG from the thermonuclear burning of a solar mass of light elements and can result in explosions that leave behind either a neutron star for weaker explosions or a black hole for stronger explosions. The remnants of these explosions match the observed properties of stripped envelope supernovae and produce massive black holes consistent with those detected through gravitational wave observations by advanced LIGO. Some research also suggests that metallicity plays a significant role in black hole formation, with lower metallicity stars more likely to form black holes, a relationship that helps explain the detection rates of binary black hole mergers observed through gravitational waves. The relationship between a star's initial mass and the mass of the resulting black hole follows complex patterns that astronomers continue to refine. While earlier models suggested a simple threshold where stars above 8 solar masses formed neutron stars and those above 20 solar masses formed black holes, current understanding points to a more nuanced relationship. Modern models, such as that described by Yamaguchi et al., propose curved relationships where a star of 20 solar masses might produce a black hole of approximately 2 solar masses, while a 100 solar mass star could generate a 10 solar mass black hole. This nonlinear relationship reflects the complex interplay of nuclear processes, mass loss through stellar winds, and explosion dynamics that determine how much matter remains gravitationally bound during the formation process. The distribution of stellar mass black hole masses observed in our galaxy clusters predominantly between 5 to 15 solar masses, though recent gravitational wave detections have revealed significantly more massive specimens, with some component black holes in merging systems exceeding 30 solar masses. These unexpectedly massive stellar black holes have prompted astrophysicists to reconsider models of massive star evolution, particularly examining how factors like metallicity and rotation might allow for the formation of black holes substantially more massive than previously anticipated. The formation of stellar mass black holes represents one of the most dramatic transitions in the universe, where matter undergoes an irreversible collapse into regions of spacetime from which not even light can escape. The multiple pathways to black hole formation, direct collapse, supernova with fallback, and alternative mechanisms involving accretion or thermonuclear processes reflect the complex interplay of nuclear physics, gravitational dynamics, and stellar evolution that govern these extreme cosmic events. Modern observations, particularly through gravitational wave astronomy, continue to challenge and refine our understanding of black hole formation, revealing specimens more massive than previously thought possible and providing insights into the relationship between progenitor stars and their compact remnants. As astronomers develop increasingly sophisticated simulations and observational techniques, our understanding of stellar mass black hole formation continues to evolve, offering profound insights into the life cycles of massive stars and the fundamental forces that shape our universe.